So, welcome once again to the course on convex optimization. Good evening to all of you, those who are viewing this lecture. If you remember, in the last lecture I had asked you this simple question, not simple, but the question is simple, maybe the answer might not be, that if you consider the function f x equal to absolute value of x, of course, x is in the real number, then at x equal to 0 the function possesses a minimum, while you also know from very simple calculus that it does not possess a derivative at x equal to 0, because the derivative when you approach from this side that is minus 1, when you approach from the other side this one is plus 1. So, left and right derivatives are different, left derivative being minus 1 and right derivative being plus 1. So, derivative does not exist. Then how, if you are faced with such a function, and observe that if you look at the epigraph of this function naturally is a convex function. The question is, how would you really talk about the derivative when the derivative is actually absent? Can you really talk about the derivative? This issue was solved by introducing the notion of a subgradient. Let us intuitively motivate the notion of a subgradient. Now, what is the derivative? Derivative is nothing but the slope of the tangent drawn at a given point on the graph. So, if you are finding the derivative at of function at x, then at the point x f x, if you draw the tangent, if you have a nice function like this, if you want to find the derivative of the function at this point, you draw the tangent at the point x f x, maybe I should be a bit more nicer, and then the slope of this tangent, basically tan of theta, is your derivative. Here we cannot talk about such a single nice tangent. For example, at x equal to 0, you can say, okay, this line is a tangent, this line is a tangent, okay, equally correct, because they are not touching the body of the epigraph, and they are just touching the curve at this thing at only one point, x equal to 0. X equal to 0 itself, this line y equal to 0 itself is a tangent, while of course, this is not a tangent, there could be. So, any line whose slope is varying from minus 1 to plus 1 is a tangent. You can say that they are tangents. So, because this is minus 45 degree, this is plus 45 degree. Now, what does a gradient satisfy for a convex function? If a convex function is differentiable, then we have this by now well known formula for you also. Now, here if I consider each of the lines is a tangent, each of these dotted lines are tangent, then if you observe that all of these tangents are lying below the graph. So, which means that if I consider for this case the slope for this particular function f, the slope of each of these graphs, each of these lines, then you will have this formula f y minus f x, some sort of slope which we are let us write it as some xi into y minus x. I am writing xi into y minus x because we are in the real setting. So, if my f is a function from R to R, just like the one above, this is what I am actually getting, because I am considering each such line, and here there are infinite such lines varying between minus 1 and plus 1. So, any number that is lying between minus 1 and plus 1 is a slope to any one of these lines. So, given a number between minus 1 and plus 1, there is a tangent line to the graph at x equal to 0 whose slope is that particular number. So, such a xi is called a subgradient. So, in general when you come for a function from Rn to R, a function which is convex. So, here x what I am talking about is x equal to 0, because here I am looking only at the tangents at 0. The subgradient at x is a vector xi in Rn. Do not confuse with this xi was in R. Okay, if you are confused, I would just rub it off and maybe I will give it a new name. Instead of xi, I call any v element of Rn such that f of y minus f of x is greater than equal to v times y minus x, and this should be true for all y in Rn. You observe that this fact what I am writing down has to be, because this is true for every pair x y. So, if I fix my x equal to 0 here, then for every y this relation actually holds. So, this is actually true for all y in R. So, this v is what is called a subgradient. This v is my subgradient. Now, the question would be which v would represent the gradient. There are many v's, many competing v's. You see there are many competing v's here, and I can claim, okay, this is my favorite v and I want this to be the representation of the gradient when the gradient is actually absent. Somebody comes along and says, no, that is not fair, you know, x equal to 0 is the minimum, then 0 must be equal to the gradient. So, this y equal to 0 line should be the gradient. So, this can be resolved by taking a more holistic view of the thing and making a amazing jump in the imagination. This jump is one of the most fundamental advances in optimization in the past few decades. Though people will not compare it with the interior point revolution which took place in linear programming, which we will talk about later in the course, but this is of immense importance to the development of convex analysis and convex optimization theory in general. So, people said, okay, let me put all the subgradients in one set and I call that set the subdifferential of f at x. So, how the subdifferential looks like? It consists of all possible v in Rn which satisfies the property fi minus fx bar is greater than equal to v times y minus x bar for all y in Rn. So, I collect all such possible v's. So, in our possible this scenario of fx equal to mod x function, or maybe I should write it like this, del of mod at 0. This is nothing but the collection minus 1 to plus 1. So, this is the subdifferential of the absolute value function. So, this is what it means. If I go by this, then this is what is the subdifferential. Now, the interesting part of this is that, okay, you have done this, but observe there is something very important. Now, I have made a very important leap. My gradient is no longer a vector, my gradient is a set. So, given an x bar, my gradient is not a vector, but a set. So, I am taking a vector in Rn and by the subdifferential or something which I am claiming to replace the gradient of a convex function where it is non-differentiable by a set. So, such mappings are called point to set mappings. or set valued mappings or multi-valued mappings, whichever you want to call them. Now, why such a choice is correct? Why do you think that this sort of approach is a correct approach? See, whatever we do, even if we come to the realm of non-differentiable functions, we have to note that the Fermat's law for optimality, that is when you have a differentiable function and f has a local minimizer at x bar, this is the fundamental rule that it should at least follow, it should satisfy this. So, if I am trying to figure out the subdifferential at a point of minimization like this particular case, then 0 somewhere must be lurking inside this subdifferential, and here we are observing that 0 which means that this is really, or this is a true extension of the gradient for the at the point of non-differentiability for a convex function. So, you now see the optimality condition changes. The necessary and sufficient condition, optimality condition, is the following. It now changes from an equation to an inclusion, to what would be called as a differential inclusion. So, x bar is a minimum of a convex function if and only if 0 belongs to this. Now, any mathematically sensible person would ask me, okay, you are talking about 0 belong to a set and all this blah blah stuff, but what if such a set is non-empty, empty? The important fact now comes to forth, that when f is a convex function from Rn to R, then this is not equal to 0, then this is not equal to the empty set, not 0, sorry, this is not equal to the empty set for all x in Rn. So, this non-emptiness is a very very important part. So, all this what we are telling makes sense. So, whole of convex optimization, the optimality criteria is actually nothing but trying to tell this in many ways. In fact, our recent book that I want to show you, which has come out in convex optimization with myself being one of the authors, is that this book where I am also one of the co-authors with Dr. Dhara, professor at IIT Gandhinagar. You see that this symbol 0 belonging to del fx, this symbol has been in the cover. So, in some way we are trying to say that whole of convex optimization, this book is on optimality conditions in convex optimization. This symbol, by giving this symbol on the cover, we are as authors were trying to say that optimality conditions in convex optimization is essentially this story. So, here we are at the very heart of convex optimization theory. Now, once I know this necessary and sufficient optimality condition, let us try to prove this. Okay. Now, let x bar be a global minima. You know, in convex optimization there is nothing like a local minima. Let x bar then x bar be a global minimum, then f x minus f x bar is greater than equal to 0 for all x. This simply implies that f x minus f x bar is bigger than the inner product of 0 vector with x minus x bar. And this simply says, because this is nothing but equal to 0, this simply says that 0 belongs to del f x bar. Now, I know that if 0 belongs to del f x bar, by the very definition of a subdifferential, I would have f x minus f x bar greater than equal to 0 of x minus x bar. So, 0 being the subgradient. So, this would immediately imply that f x is bigger than f x bar for all x. This is true for all x in R n, of course. The next natural question would be, okay, this is for unconstrained case. If I have to minimize a convex function f x over x element of C, how do you talk about necessary and sufficient optimality condition, and I do not have differentiability of the function, say at the even at the minimum point. Now, how to handle this thing? So, let us think it over, let us be a bit intuitive. If this was differentiable, the optimality condition is both necessary and sufficient. Of course, f is a convex function, C is a convex set. In our study, we have to be very careful, unless and until mentioned, the functions are always convex and sets are always, the functions are always convex, the sets are always convex and usually closed, unless specifically told to be open. So, this is so if grad f x minus f x bar, you have I think I have not done this thing. So, the optimality condition that we know, that if f is differentiable, then x bar is optimal if and only if for all x in C. Now, the question is, if it is not differentiable, how do I replace it with the subgradient? Okay, let us make a guess. Guess is the following: there exists xi, some xi, I do not know what it is, in del f of x bar, such that xi times x minus x bar is greater than equal to 0 for all x element of R n. How do I prove this? You might try to do it in the way we have done it for differentiable case, but remember, there is nothing like a Taylor's theorem that you have seen in the non-differentiable case. In order to do so, get an idea of this, we shall refer back to what is a different approach to non-differentiability of a convex function, but ultimately would be linked with the subdifferential notion, that is the notion of a directional derivative. So, how do you define a gradient? What happens if you write down the Taylor's expansion? So, if the function is differentiable, then if you write down the Taylor's expansion, then you will have this lambda v minus, okay, I have been using v for subdifferential. So, let me put h, a lambda is greater than 0 possibly, for whatever, some lambda. I am just writing down the definition of derivative in the, so limit as lambda goes to 0, because I will divide by lambda on both sides, this will vanish and this is what I will have. Now, here lambda is supposed to go both from the right hand side to 0 and left hand side to 0. It could be an increment in any direction, does not matter. But for a convex function, this thing may not always happen. Again, go back to the prototype example. So, look at the point 0, x equal to 0. Prototype example, f x equal to absolute value of x, x is in R. So, let us look at this in this particular case x plus lambda h, x is 0 minus f x by lambda. First I take lambda from the right hand side, this side lambda going to 0. So, this will be f of lambda h minus f of 0, which is 0 by lambda. So, this will be lambda of mod h by lambda, which is mod h. So, limit of so what I have done, I have made an increment along a given direction h, along a given vector h. So, I have moved from x, I have moved a little bit along a vector h. So, this sort of derivative is usually called the directional derivative. Now, if the function is differentiable, then the directional derivative is equal to, as you can see from the Taylor's expansion, is equal to the inner product of the gradient and the direction. So, this sort of limit is usually called a directional derivative. So, lambda goes from the right side 0 plus. So, in this particular case, this is mod h. Now, when it will go from the left one, so both these two limits do not agree, and so I cannot say anything about differentiability, and which you know that is not differentiable. So, the directional derivative in both ways do not agree. So, directional derivative in this sense of the limit being taken both ways need not exist for a convex function. So, directional derivative in both sided sense need not exist for a convex function. But an important thing happens, the directional derivative in a one sided sense always exists for a convex function, that is, if I take this limit where lambda is only coming from the right hand side, this symbol lambda down arrow 0 means lambda is greater than 0 and lambda is going to 0. Another way of this is another way of writing lambda is 0 plus. So, if f is a convex function, then from Rn to R, then this limit, one sided limit, always exists finitely. Now, if this limit exists finitely, so what? How does it link with the subgradient? Can you give me a formula like this for the differentiable case? Is subgradient related to it like in this way? Let us figure it out. Okay. Now, by the definition of subgradient, I of course have the following formula true. that for every v in the subdifferential of x, this is what will happen just by the definition of the subgradient. So, this would imply so voila, as the French would say, because French have a lot of contribution in optimization. This is the link between the differentiable case, the link between the gradient and the directional derivative. Here we have a similar link between the subgradient and the one sided directional derivative. So, for a convex function, let us give it a particular symbol. We will call it the subgradient of f in at the point x in the direction h, and for a convex function, give me a point then and give me any direction h, this limit would always exist, or give me an h, whatever point you take, that limit would always exist. So, the directional derivative always exists. Now, which means what I have so it means for every v in del f x this happens. So, v element of del f x implies v is element of the set of all say w such that f dash of x h is bigger than w h for all h. So, if I fix this x and I keep on changing h, and for every h you take and for any fixed subdifferential you take, or for all, basically this formula holds for all h also. So, you fix up a v, then for all h this formula will hold. You fix up a h, then for all v this formula would hold. So, basically this. So, subdifferential becomes this subset of this set. So, it is all collection of all such w's which satisfies this inequality for all h. So, the next question is what is the converse? So, I am see the whole idea is to trying to parallel the differentiable case. So, I had this one. So, my question is when will I reverse it? When will that be a subset? Now, I will leave this as homework. This is indeed true. That is what you will have is that so here comes the beautiful relation between the subdifferential and the directional derivative. A lot more things to say. In fact, how do you prove this one? So, homework is prove this. So, because I have a lot more things to say about the directional derivative also, let us give you a hint, because it might not be so easy for those who are not in the subject to really prove this, because it is quite an advanced thing, because once you learn of all these things you are at the frontier of knowledge as far as convex optimization is concerned. You see, here you have to observe a very, very important fact, that if you look at this expression, let me just look at for a fixed lambda and fixed x and h. If I fix my x, fix and h, then this is nothing but a function of lambda. Sorry, I will just look into this. This difference quotient is a function of lambda. Now, as a function of lambda, as lambda decreases, as lambda goes to 0, q lambda also decreases. And then the limit of q lambda should be the lower bound of q lambda as lambda goes to 0. So, in fact, one can also write that f dash x h can be shown to be the infimum of lambda greater than 0 of the difference quotient, and this fact is fundamental to prove this fact, this inclusion. So, do take a careful note. Now, let us summarize what we have learned till now. A convex function need not be differentiable at every point. There is a good chance, and it is a generic property, that the minimum usually lies at the point of non-differentiability. The differentiability can be tackled by the introduction of subgradient and the notion of a subdifferential, which replaces the notion derivative, but we have not really shown how it replaces. Okay, we are taking it as something in lieu of the derivative, and for a convex function the directional derivative need not exist, but the one sided directional derivative exists. So, this is what we will call the one sided directional derivative. So, one sided directional derivative of f at x in the direction h, and it is also linked with the subdifferential in this fabulous fashion. So, and of course, we have the fundamental formula, which is very important, that 0 is element of del f x bar. This holds true. And so, now let us go back, let us not go back, let us just go back to have a fresh look again at the subdifferential. So, if I have the subdifferential of a convex function from R n to R at a point x bar, what are its properties? First property is that it is convex. This is homework. So, the del f x is a convex set. The second property is that it is closed. It's homework for you. Okay, those who are engineers might not be so convinced with how to prove closeness and all those things. Let it be not for the, but for the mathematics people who are watching this show, they should definitely try to figure out how to prove it is closed. It is not a very big thing. Another thing is that it is also bounded. So, this too makes it compact, because we are in finite dimension, and del f x is thus a convex and compact set. Now, how do you prove that it is bounded? That is a very important thing, but in order to prove that it is bounded, we need to know some additional things about a convex function. So, what we first should know, that a convex function f is convex. If f is convex, or I should write, if f is convex, then f is locally Lipschitz. So, what do I mean by this statement of locally Lipschitz? So, for any function f from R n to R, assume it is a convex function, and any x bar in R n, there exists delta greater than 0 and L greater than equal to 0 such that f of y minus f of z is less than or equal to L times norm of y minus z for all y and z belonging to this. So, this L is highly dependent on your choice of x bar. Basically, L depends on x bar. If you choose a different x bar, then the L changes, this L will change. This is called the rank of the Lipschitz function, rank of local Lipschitzness. Or local Lipschitzian rank, whatever you want to call it. So, this constant will change if you change your x bar, but if this constant does not change once you change your x bar, which means then such a function is called globally Lipschitz. So, any convex function, if f is convex, then f is locally Lipschitz. So, any convex function will satisfy this property. Now, this property would be used to show that a subdifferential is a bounded set. To take any xi, what do you mean by bounded? I have to prove that norm xi is less than a fixed number, say m, for all xi in del of f x bar. Now, how do I do this? So, observe this fact, xi, okay, I will just be more clear at the very beginning. F of x bar plus lambda h minus f of x bar is greater than equal to xi times lambda v. For any xi belonging to this is true, not xi times lambda v, xi times lambda h. As I is a subgradient. Now, what happens is that once I know this, I will just write it in a slightly different way, just change the sides, just change the way of writing. So, when lambda is sufficiently small, x bar plus lambda h is very near x bar. So, it is within some neighborhood which you want, and then applying local Lipschitzianness, you will get that this is nothing but lambda times norm of h. So, this is nothing but L times lambda norm of h. So, this cancels out, this lambda cancels out to give xi of h. Now, here comes the more mathematical oriented thing. Now, I can write this as xi of h. Of course, if h is 0 and h is 0, this is anyway satisfied. So, if when h is not equal to 0, I can divide. So, there is L here, I can divide it by norm of h and write this. Now, because this is true for all h, whatever h you take, this will always be true. I can take h, repeat the argument, take another h, repeat the argument. So, you can take supremum over, this is slightly mathematical, just bear with me those who are not so involved in mathematics. So, this is by very standard technique you can show that this is nothing, this is defined as norm of xi. This thing, that soup of this is nothing but defined as norm of xi, and that is less than equal to L. So, this is true for all xi. So, that shows that del f x bar is bounded. Okay. So, it has good properties. Now, what you have observed is that the directional derivative x in the direction h is always satisfying this property. So, if I fix the x and fix the h, this result is true for all xi in del f x bar. So, let me take x bar here. The question is, is this only an inequality or actually it is a equality or strict inequality holds. The beauty, and this is how the subgradient is finally linked with the derivative, is that the subgradient is basically becomes a quite a good representative of the derivative. You see here this formula. So, I can now write this is greater than equal to soup of for any xi in del f x now whether there is this can be a strict inequality or always equality holds. One of the far reaching results of convex analysis is to show that now, but because this is a compact set for a given x bar and this being a linear function, one can also write this as so. This is how truly this through this dual nature, this is how truly the directional derivative is linked with the subdifferential. So, this is one of the most important and far reaching formulas in convex analysis and has many applications. So, now let us go back to our question by which I will end today's talk. Minimize f x, right, subject to x element of C, f convex and C closed and convex function from Rn to R and C closed convex set. What is the necessary and sufficient optimality condition? Write down the optimality condition, that is what we wanted. Write down the necessary and sufficient optimality condition. Now, if x bar is a global minima, so this is my problem CP which I had already written, convex programming. So, x bar is the global mean, consider this thing x bar plus lambda x minus x bar where x belongs to C. Then by convexity of C this belongs to C, and by the global optimality of x bar, this is greater than equal to 0. Now, I can divide by lambda. Now, what I can do is I can divide by lambda now, if I take the limit as lambda tends to 0, this would imply f dash x bar x minus x bar is greater than equal to 0 for all x, you know. Basically, this is a formula, because this is true for any arbitrary x. Now, what happens? Suppose I know the fixed x, suppose my x is fixed for the moment, x is say fixed for the moment. So, this is the directional derivative, right, and this is your whatever, this is your direction x minus x bar. So, I can write that f dash of, now I will use that formula which I wrote as an important formula. So, this I can now write as f dash x bar x minus x bar is equal to max of right, this is what you can have. Now, once you have this, but this is for every x, this is greater than or equal to 0. So, for all x I will have now max of so, this is my optimality condition. Now, for every x, for each x, there exists xi such that xi belongs to del f x bar. Of course, xi depends on x. So, such that xi x of x minus x bar is equal to max of So, what I have proved that if x bar is an optimal is a global minimum of Cp, then for each x there exists xi x such that xi x x minus x bar. Now, if you go back a little bit earlier, my formula said that there exists a xi element of this. My guess was that this will happen for all xi, for all the x's this will hold true, but I seem to have got something slightly different. What is that difference? That for every x my xi x changes. Okay, there is no harm, I have perfectly deduced it. So, mathematically this is fine. From here, is this any way to go to the one I have made a guess? Is that guess right? For that we have to study a bit more convex analysis and show that that guess is right, and both this formula from here to there can be obtained and from there to here can be obtained. So, for that we have to do a little bit more study about convexity and convex analysis, and that would be taken up in the next lectures. Thank you and good night.